So we are defining norm, definition of norm. So we are going to define norm. Let X be a linear space over a field K. So you will let X be a linear space over a field K. This field K may be R or C, a set of reals or set of complex numbers. Field R or C.
X be
a norm on X.
X be a linear space.
Norm on X
over
is a function from X to R, a set of reals, and it is denoted by norm. This is the notation. So actually norm of X is a function from norm is a function from norm is a function from X to R. So it's a function from X to R satisfying three conditions.
This is the notation.
First one is,
so actually norm of X is a function from
all X
norm is a function
y
from
in X, X comma y in X.
So, norm is a function from
and K in K
is a function from X to R
in K.
So
norm of X
is a function from X to R
satisfying
by
three conditions.
This is the notation.
First one is, and so this is the first condition. Norm of X is greater than or equal to 0, and norm of X is equal to 0 if and only if X is equal to 0. So this is the first condition. Second condition is famously known as triangle inequality. So this is norm of X plus Y. This is less than or equal to norm of X plus norm of Y. Norm of X plus norm of Y. And third condition is norm of K times X. This is equal to modulus of K times norm X. So a function norm on X is a function from X to R. It is denoted by this. So it is a function from X to R. For all satisfying these conditions, for all X and Y in X and K in K, it satisfies these three conditions. Then we say that this function is a norm. And on a linear space, if you are able to define a norm on it, then that space is called a normed space. So a normed space is a linear space with a norm on it. This is a linear space with a norm on it is called a normed space. You can take any page. So we want to create a new page. Now, suppose we are going to define a metric. So for x comma y in X, we define let d of xy to be norm of x minus y. d of x by dt, norm of x minus y. Then d is symmetric on x. You can verify that. Then d is symmetric on x. This is symmetric on x. And we have this condition, modulus of norm x minus norm y. This is less than or equal to norm of x minus y. So norm of x minus y. Norm of x minus y for all x comma y in x. For all x comma y in x, we know this condition holds. Therefore, the function, so you have the function, this one satisfies this condition. You have this function satisfies this condition. Therefore, the function norm is uniformly continuous on x. And further, suppose xn converges to x and yn converges to y. Yn converges to y in x. And kn converges to k. And kn converges to k. This will imply that xn plus yn converges to x plus y. Xn plus yn converges to x plus y and knxn converges to kx in x. Kx in x. This is usually referred to as the condition, continuity of addition and scalar multiplication. This is known as continuity of addition and scalar multiplication. Now we are going to define various types of norms on Kn. So we are going to discuss some examples. You consider the space Kn. So we are going to define different types of norms on Kn. So as a first case, you consider n equal to 1. Then the space, so the corresponding space is K itself. K is the space itself. K is the space. Then you know absolute value. So K is R or C, and you have absolute value function is a norm on K. So absolute value function is a norm on K. So absolute value function is a norm on K. And further, you know that you have this one. You have norm of K is equal to, we can write it as K times 1, and using the definition it is modulus of k times norm of 1. So suppose any norm on k is a positive scalar multiple of the absolute value function. So here this is you can say that this is a positive scalar multiple of the absolute value function. So we can express norm k in terms of the absolute value function. So any norm on k is a positive scalar multiple of the absolute value function. So that is one of the interesting thing. And for n, so you create a new page. For n greater than or equal to 1, there are a variety of norms on Kn. So for n greater than or equal to 1, greater than 1, greater than or equal to, for n greater than 1, there are a variety of norms. We are going to define that. So we are going to describe some norms. There are variety of norms. Variety of norms on Kn. So we are going to define different types of norms on Kn. So you let P be, so these are the examples that we are going to discuss. So you consider, so let P be a real number greater than 1 or equal to 1, be a real number. P greater than or equal to 1 be a real number, and for x equal to x of 1, x of 2, etc., x of n in Kn, you define P norm of x to be P norm of x, or you define a norm like this. We are going to prove that it is a norm, P norm of x to be x of 1 is modulus x of 1 plus x of 1 raised to p, modulus of x of 1 raised to p plus modulus of x of 2 raised to p plus etc. plus modulus of x of n raised to p, the whole raised to 1 by p, whole raised to 1 by p. So suppose you define a norm like this, and when p equal to 1, you are getting, so we are going to discuss different cases. So suppose p equal to 1, p equal to 1, then the norm is known as the 1 norm. Corresponding norm is known as the 1 norm. Then we have 1 norm of x. Remember, x is x of 1, x of 2, etc., x of n. So this is actually equal to modulus of x of 1 plus modulus of x of 2 plus etc. plus modulus of x of n, modulus of x of n. And you can see that this is a norm. 1 norm is a norm. Then 1 norm is a norm. We are going to prove that For example, so we have to check three conditions. One, norm of x1, one norm of x is greater than or equal to 0. Since you know that each of the components xi, each of the components xi has positive modulus, so their sum will be also be non-negative. So since norm of x of I is greater than or equal to 1 for I is equal to 1, 2, etc. n, I is equal to 1 to etc. n, we can see that norm of x, one norm of x is always greater than 0. So we have, and you know norm of x equal to 0, one norm of x is equal to 0 if and only if the sum x modulus x of 1 plus modulus x of 2 plus etc. plus modulus of x of n is 0. This is 0. And you know this is sum of non-negative terms, and this is 0 implies, this implies, or this is if and only if x of I equal to 0 for each I is equal to 1, 2, etc. n, x of I equal to 0 for I is equal to 1, 2, etc. n. That is x of I equal to 0 for I is equal to 1, 2, etc. n is implies x equal to 0. That is one norm of x equal to 0 if and only if x equal to 0. So this is how. And you can now check triangle inequality, so for which you take a new page. So one norm consider, so you let x to be x of 1 to be x of 1, x of 2, etc. x of n. So suppose that this is first element, and suppose y equal to y of 1, y of 2, etc. y of n, y of 1, y of 2, etc. y of n. So you can define x plus y as component wise addition. So this is x of 1 plus y of 1, etc. x of n plus y of n, etc. x of n plus y of n. So you consider one norm of x plus y. By definition, this is equal to modulus of x of 1 plus y of 1, y of 1 plus etc. plus modulus of x of n plus y of n. So we have this x of n plus y of n. So this is equal to, and you by applying triangle inequality on the components, you have this is less than or equal to modulus of x of 1 plus y of 1 plus etc. plus modulus of x of n plus y of n. Modulus of x of n plus y of n. So how? X of n. So modulus of x of n plus modulus of y of n. And this is equal to modulus of x of 1 plus etc. plus modulus of y of 1, sorry, x of n x of n plus modulus of y of 1 plus etc. plus modulus of y of n. etc. plus modulus of y of n. And you have this is equal to 1 norm of x plus 1 norm of y. 1 norm of x plus 1 norm of y. So you are getting norm of x plus y, 1 norm of x plus y, this is less than or equal to 1 norm of x plus 1 norm of y. 1 norm of x plus 1 norm of y. And now you have to check the last condition, what is k times norm x. So consider k times norm x, 1 norm of k times norm x. So this is equal to modulus of kx1 plus modulus of kx2 plus etc. plus modulus of kxn. Modulus of kx1 plus etc. So this is, you can take, so this is actually equal to modulus of k into norm x, modulus of x1 plus etc. plus modulus of k into norm xn, and you can take modulus of k outside, and this is into norm x1 plus etc. plus norm xn, and that is equal to now since norm, one norm is a norm on k. So that is the case when p equal to 1. So you consider, let p be greater than 1. Let p be greater than 1. So what is the definition of norm then? Norm of x is, p norm of x is sigma I is equal to 1 to n x of modulus of x of I raised to p the whole raised to 1 by p. So this is the definition of raised to 1 by p. So this is the definition of p norm of x. Now you have to show that it is always positive and always non-negative. So we have p norm of x is greater than or equal to 0, since you have each term, this is equal to 0, since you can see that each term of the sum, this is sum, each term of this sum, this is positive, so it's raised to a power is positive, power p is positive, whole raised to the sum is positive, etc. So you have, this is because since x of I, modulus of x of I, is greater than or equal to 0 for all I, for I is equal to 1, 2, 3, etc. n. So you know that this is greater than 0, and we consider p norm of x equal to 0, and you know p norm of x equal to 0 if and only if the sum this sigma I is equal to 1 to n x of I raised to p the whole raised to 1 by p, this is equal to 0, and this is equal to 0 if and only if each term modulus of x of I is equal to 0, because you are summing a positive terms, raised to 1 by p. So this is raised to 1 by p, this is 0, and x of I equal to 0. So this sum is equal to 0 if and only if each x of I equal to 0 for I is equal to 1, 2, etc. n. So this implies x equal to 0, because you know that x is actually x of 1, x of 2, etc. x of n. So this is x equal to 0, and this, that is, you are getting this condition p norm of x equal to 0 if and only if x equal to 0. P norm of x equal to 0 if and only if x equal to 0. Now, to prove the triangle inequality, you require Minkowski's inequality. So, you have to prove the triangle inequality P norm of x, have to prove the triangle inequality P norm of x plus y, P norm of x plus y less than or equal to P norm of x plus P norm of y. This is what we are going to prove. Now, we use Minkowski's inequality. You have Minkowski's inequality this one for 1 less than or equal to p less than or equal to infinity, for 1 less than or equal to p less than or equal to infinity, you have this sigma j is equal to 1 to n modulus of aj plus bj whole raised to p the whole raised to 1 by p, whole raised to 1 by p. This is less than or equal to sigma j is equal to 1 to n modulus of aj raised to p the whole raised to 1 by p plus sigma j is equal to 1 to modulus of bj raised to p 1 by p. So now this inequality, Minkowski's inequality. So using this you can angle inequality. Prove triangle inequality. So let x is equal to x of 1, x of 2, x of 3, etc. x of n. Y is equal to y of 1, y of 2, etc. y of n. So this is your x and y. Consider x plus y, p norm of x plus y. So you have this is equal to sigma j n modulus of x of j plus y of j the whole raised to p the whole raised to 1 by p, whole raised to 1 by p, and this is less than or equal to, by Minkowski's inequality, this quantity is less than or equal to sigma j is equal to 1 to n modulus of x of j the whole raised to p the whole raised to 1 by p plus sigma j is equal to 1 to n modulus of y of j the whole raised to p the whole raised to 1 by p. So that is actually, this is equal to p norm of x plus p norm of y. p norm of x plus p norm of y. So you have a duality now. So that is x plus p norm of x plus y. This is less than or equal to p norm of x plus p norm of y. It's p norm of x plus p norm of y. And you have one more condition left. That is p norm of kx. It's p norm of kx. You know this is equal to sigma j is equal to 1 to n modulus of k into x of j the whole raised to p the whole raised to 1 by p. Whole raised to 1 by p. So you have this is equal to, you can take modulus of k outside, so this is equal to modulus of k. So we can a little bit more expand more. This is equal to sigma j is equal to 1 to n of k raised to p the whole raised to 1 by p into x of j. So you can take, so sorry for this. So how this all raised to 1 by p. So all raised to 1 by p, and that is equal to, you can take modulus of k raised to p outside from the sum, then you take 1 by p, so we are getting modulus of k, you can take that outside into sigma j is equal to 1 to n x of j modulus of x of the whole raised to p the whole raised to 1 by p. So that is nothing but modulus of k into norm p norm of x. P norm of x. So you have proved that all can be false. So from that we can conclude that this one p norm is a norm on Kn for p greater than or equal to 1. So we have proved that this is true for p greater than or equal to 1. And you know norm 2, a 2 norm. So you have 2 norm, and this is not usually called the Euclidean norm. And it is defined like this. So this is known as Euclidean norm. It's known as Euclidean norm. It's defined like this: norm of x for x belongs to 2 norm defined as sigma j is equal to 1 to n x of j the whole square the whole raised to 1 by 2. So this is known as the Euclidean norm, usually called the Euclidean norm. And you have one more norm on Kn. We are going to discuss one more norm on Kn, and that we will discuss in the next class. Thank you.